Welcome to Pitfalls Part 2. Let's take a look at some more possible potential problems when dealing with thinking particles. One of them has to do with generators, and generators have a random seed value associated with them. In this case, we're going to look at what happens when two generators have the same random seed. This is a particle draw creating some red particles, and another particle draw creating some yellow particles. And these were both created drawing left to right as we created those particles. And what we're going to see then is we go ahead and assign their parent group colors. We assign them a shape and a size. But we add some size variation here. And we notice that these particles are kind of varying themselves in a pattern. They have corresponding size changes between each of them. You see these third pair here is they're all kind of resizing themselves. So the variation is not really all that unique. Of course, what we need to do then is modify the random seed of the generator. And in this case, we'll go ahead and scrub. And now when we start to increase the size variation here, we can see that it breaks that connection between those randoms. And so now we get kind of truly random sizes for these particles. We'll go ahead and also adjust the red. And so now we can definitely see that when the random seeds are different, it's going to process that variation much differently and give a better result. So just remember, if you're dealing with a generator or even also a random helper, go ahead and adjust its seed typically whenever you create it, just so that you can ensure that you're getting completely unique values out of that operator or generator. Okay, so that is one part of what we want to look at. The next kind of gotcha has to do with wiring in serial versus parallel. And this is something we see quite a bit with thinking particles. There's a perception, I guess, or a workflow issue when dealing with particle groups that we have to make sure we understand. And that is when we want two different particle groups, in this case red and yellow, to interact with each other, we have to be very careful about how we approach that. There's some standard operators that solve these problems, but first let's go ahead and take a look at how people generally immediately try to deal with multiple groups at the same time. What they'll do is they'll go ahead and create, and we'll switch this other p-pass to yellow group. They'll go ahead and create two group references out here. And then let's say what we want to have happen is when the red and the yellow get close enough to go ahead and create some green particles. So what you might do is take a distance condition and feed those particle connections in there. And remember that when we feed just a particle data type into a position, it automatically takes that particle's position and feeds it to this data type. There's that auto conversion of data types. But anyway, so the red particles and the yellow particles, let's say when they get within a distance of 10 of each other, then we want to go ahead and create some green particles. And we'll just create a pistol shot per call with a small lifespan, lots of direction variation, and say no speed, but we will give them some emission, distance, and variation just to kind of vary it up. So let's go ahead and say, okay, when this happens, go ahead and create those green particles. And let's go ahead and look. We need to actually control the position of where that occurs. In this case, let's just go ahead and feed the red particle. It's going to use the red particle's position and create those green particles at that location. So let's go ahead and see. Now they move past each other, of course, and they are on the same plane. They're on the the XY plane. So the problem here is that we have these two separate p-pass operators both feeding information into this distance condition into some other operator. And the problem is that we cannot technically do this. The way the thinking particles logic works is that when we have this red p-pass group reference here, it's going to take all red particles and for every time sample, it sends out each particle, each piece of particle information to all the requesting operators. And when we wire in parallel, this is called wiring in parallel like this. When we wire in parallel, there becomes a disconnect where all these red particles start processing themselves and sending out information, and then kind of in a separate data stream, all the yellow particles are also feeding out all their information. So these two never really have a chance to sync up and properly compare themselves. One of the kind of brute force hacks that you can do is expose the on input for this other PPAS group and feed that particle, the red particle, into that on. And what this does is it says for each red particle coming out of here, and there's 4 of them, for each red particle, go ahead and turn on and reference each yellow particle, or call that particle. I don't want to confuse you. There's an entire reference operator, and that's not what we're talking about. Basically, each and every red particle is going to send out a call to every yellow particle. So red particle number 1 calls each and every yellow particle, and we'll send out all of their information now. So this is kind of how we wire it in serial. So we actually control this second PPAS operator. So now as they become closer, we can see all those green particles appear. And of course they're a little wacky like that because they have a low lifespan. But okay, so that does work. Unfortunately, it's possible, but it's not the best workflow. One of the better workflows that we would want to do is not wire in serial like this with 2 separate PPASs. What we really want to do is we want to go ahead and use the PPAS AB initiator, which, let's go ahead and we will copy all this information. What we're going to do is we're going to say interaction bad serial, and we'll disable that rule, and then we'll create a new dynamic set here called interaction good PPAS AB. And what we'll do then, this way we can actually leave this kind of logic here in the file, and this dynamic set's disabled, so it'll be ignored by the processing. And then we'll go ahead and just kind of rewire what we need to do in here. And PPAS AB, what we do is we need to do a comparison between red and yellow. So we'll set group A in PPAS AB to be red and group B to be yellow. And there's a whole bunch of different parameters here. We have a specific video that talks about PPAS AB, so we'll refer you to that for those settings. But basically what we're going to do is we're going to remove this entire distance operator and go ahead and just have PPAS AB do that distance comparison for us. So any of these 2 particles groups who are within 10 units of each other will go ahead and these outputs will become active. And that's kind of an important distinction with PPAS AB, is that whatever conditions we set up here, these have to evaluate true in order for all of these outputs, in order for them to fire off their information and be sending anything out. If the condition's not true, if the red is not close enough to yellow, there is no A output for that particle. And it is important to say that PPAS AB, it takes, much like we did here in serial wiring, it takes each and every red particle, each distinct one, and does a comparison, or tries to do a comparison based on the parameters we have with each and every yellow, or whatever the conditions are. Okay, so in this case, we can just set that distance to 10, and then we'll go ahead and say we'll control when this position born occurs by connecting the A particle. So that A particle connection is also going to tell this position born to create these green particles at A's position. So let's go ahead and scrub again, and there we see pretty much the same result as we saw with serial wiring. Just remember that PPAS AB or psearch are much better ways than having to reference other particle groups like this and trying to wire them in serial. Not such a good practice like this. It works, but the preferred method is PPass-AB. Okay, the next example that we want to take a look at is example 2 in this file. And we're going to go ahead and just save and update this file. This has to do with, let's actually zoom out. Are we not seeing, what do we have? Okay, we suffered a gotcha ourselves, a little pitfall. We have some particles being created, but they do not have, and you can see them there because we select that particle draw operator. It will show you point locations where these points will be created. But if the operator is not selected, it does not. And the gotcha that we just suffered was that our master dynamic is set to show mesh and display no particle dots. So here in this example 2, these particles actually do not have that rule that assigns them a shape and size. And so these particles are out here right now, we just don't see them. So we have to remember to watch out for our display settings. We'll go ahead and disable, force this setting. Let's go ahead and set the global display type to dots. Okay, so now we get a whole bunch of dots here. It's very Christmassy. And what we want to take a look at is, let's go ahead and see. Yes, we want to control, and this is a little more advanced kind of topic, I guess, but we want to control when comparisons happen with PPass-AB such that we're able to limit when those comparisons do happen. That's not the best explanation, but you'll see here in a moment. What we've got, let's go ahead and turn off that comparison rule. We've got a particle draw operator that's creating 9 of these particles out here. Let's take a look at that grid. These are 10 units per grid. And what we're doing is we're doing a comparison. We've got a comparison rule with a PPass-AB, and we're comparing all red particles with all red particles. So it's doing a comparison within the same group, but it's doing that comparison only when those red particles are within 25 units of each other. So let's go ahead and take a look. We'll just do a little quick line draw and check our distance down here in the status update. So the distance of 25 is about like that, so that whole radial. So this particular red particle right here will be able to compare to this one and this one, but it will not reach that one. It's a little too far. And what we're doing is we've got a little rule set up that feeds out those particles into a vector input of an expression operator. And basically all this does is it takes these particles' position. It's got a little bias scalar that it can use, and it basically averages their positions, and then we're feeding that position information into this position born, who's creating the green particles. The problem that we want to take a look at is the fact that we see all of these, we see 2 greens instead of what we want to see is just 1. And what's happening here is these comparisons between red are happening in both directions. It's important to understand that with the PPass-AB when it's set to the same group. Each and every red particle is checking against that particle, and then this particle is also checking against this particle. And so both of these evaluate true. They're both within 25 units of each other. Let's go ahead and cancel there. So what we want to do is, in this particular case as an example, we want to show how we can limit this PPass-AB so that this comparison only results in 1 green particle being created. And the simplest way to do that, I'm going to go ahead and we're going to show particle IDs, and let's turn off debug mode. The simplest way is to actually rely on the particle ID integer itself. So TP assigns a unique PID to each and every particle. What we can do then is we can say, okay, well, we're comparing red particles with each other. Let's take a case where 1 is comparing against 2. And then we have to remember that because of the way PPassAB works, it's taking each and every red and comparing it with each and every other red. So not only does 1 compare with 2, but 2 compares with 1. So we want to make sure that those comparisons only result in one green particle in between. And the easiest way to do that then, rely on the particle ID and do a test on those particle IDs. And we can do kind of just a simple greater than test. So if this particle ID is greater than this particle ID, then go ahead and create something. But if we compare 1 versus 2, well, the ID number of 1 is less than the PID of 2. So we can prevent that from resulting in a new green particle there. Okay, the way we can do that is simply a condition where we've got a black box under M3D conditions called greater than. And greater than just does a little expression test. If A is greater than B, then output a 1, meaning true, or output a 0 for false. So we can go ahead and just feed A particle into the A input and B particle into the B input. So now it's going to do a comparison of those values. And we'll go ahead and pipe that output boolean and control this position borns on input. Okay, so go ahead and watch, and as we update the viewport here, watch what happens. Now we're only getting one particle in between each of the pairs, which is going to be very useful for us later when we start dealing with TP joints. So that's kind of the whole purpose of showing this comparison system. Okay, let's go ahead and do a little bit of extra work on this. We want to go ahead and actually look at what's happening with this data, and go ahead and expose certain data types to take a look at their output. Actually, let's do this. Let's reset that and go to 0. So even on frame 0, TP is evaluating, of course, and we're going to go through the debug log and take a look at what is happening. So PPassAB is sending out first. Well, first it's important to know, here we are at time 0. This is all the data that's being calculated here at time 0. What's happening is PPassAB, it's sending out particle pairs who meet this condition within 25 units of each other. And so we're seeing first a comparison between 0 and, which is a red, and then also, because PPassAB is also red, it's comparing it against particle 1. And because 0 is less than 1, it is not greater than, so this output is going to be false. And so we see that greater than test output called condition, and this means output like that. That results in a 0. So of course there is no particle created. Let's go ahead and spice this up just a little bit more. Let's go ahead and add a memory operator, which is our favorite debugging tool. And we're going to go ahead then, and once that's connected, that's all we need. What we can do is go ahead and reveal this born particle information to debug. Let's go ahead and jump back one frame to the beginning. Okay, so as we were saying, it's doing all these comparisons. A compared to B results in 0. We've got 0 against 3 results in 0. But let's go ahead and take a look at the case where it does output true. And what we get here is all we have to do is look for the born particle output value. So it's a little confusing because there's an extra piece of data being sent out. Debug does that anytime an output's being called. If it's being called multiple times, it can end up being shown. It will show up here in the debug log multiple times. But in our case, let's just take a look. PPassAB's A particle coming out is a 1, so it's this guy, is comparing against the B particle output, which is 0 ID, which is this one. Well, that is going to result in a true value, and so what happens is we get this born particle 9 appearing here. There must be some kind of order of operation issue where maybe it's the greater than should be above that position born. Let's check that. Still doesn't seem to matter. The greater than is being reported ahead of that other information here in debug. We'll have to take a look at that. But basically, you can understand how we are checking that PID to kind of check, hey, if A is greater than B, then only allow this to happen. So this is just one way that we can kind of control the number of comparisons and the result of those comparisons. Okay, to wrap up this video, we're going to go ahead and take a look at just two other fairly lightweight gotchas or pitfalls. The first one has to do with data channels, and data channels on particles. We're able to go ahead and we'll add a data channel for this particle group, the red group, and we're going to call it test 1. And so you can see here this channel 0 then becomes test 1, which is all fine. Let's say we came down and we had a specific rule then that is going to assign to the red particles. We're going to assign a value into their data channel. That data channel needs to be set to the data channel we're going to assign it to. And here on the red group we can see that channel 0. And the data channel will expose the float input, and we'll just have each of these red particles generate a random number, and we'll store that random number here in the data channel. Okay, so red's got a data channel. The problem that you can run into sometimes is that if you start adding data channels to parent groups and sometimes other groups, but if you add them to parent groups, watch what happens. We're going to call this test 2, and we go ahead and add this data channel to the colors group. And so that colors group now has its own channel 0 called test 2. But because of the way data channels are inherited by child groups, what we get on the red particle group then is that its channel 0 is now set to test 2, whereas previously it was set to test 1. So when we end up assigning red's data channel here, this one's still set to 0, and it does not automatically update to account for that new data channel on the parent group. So that's something to watch out for when you're dealing with a lot of data channels. Be aware that if you make any changes to your data channels or add new data channels to parent groups, it's going to offset the channels for children groups if those child particle groups already had data channels. Okay, that's pretty easy to understand. One of the other ones that we want to look at is has to do with memory operator. And memory operator is a fantastic operator. It allows us to store all different kinds of information for particles with depth. We've got a whole video that talks about this, so check that out. But one of the problems that we can run into is if each, actually let's not do a scalar, let's do not a vector but a scalar. Let's go ahead and store this scalar in here. We'll go ahead and just use this same random setup. So now, let's go ahead and delete that. We don't need we'll leave those data channels in there so they're in the file. But the memory operator problem that we can run into, we've seen maybe once or twice before in some of the previous videos, is that if you ever shift and drag a memory operator out here, it will end up creating a duplicate, of course, but part of that duplication includes creating a duplicate variable. So now if we were to call in a separate memory operator and we wanted to get that scalar value, well, which one do we choose? We're going to have quite a bit of problems now because of that. So it's very important when dealing with memory to keep all your variables carefully managed in your particle groups, because you don't want that confusion of having multiple variables. Same thing happens if you duplicate the dynamic set. Hold shift and drag that dynamic set, it creates a duplicate. It's also then going to duplicate that memory and all of its variables, which is going to cause problems when we try to pick, hey, which one is it? Of course, one of the solutions there is to actually rename your memory. If we can get that rename going. Rename it something distinct. We like memory key since it's key value, or main, or something important in it. So now when we come to our other memory operator here, we can say, okay, well, I know memory key is this specific memory operator right here because it shows us the title and the name of that specific operator, whereas this other memory operator, which is the one down here in this dynamic set, it does not have a unique name, and so we can identify it there. Okay, let's go ahead and get rid of that dynamic set. One of the ways that we deal with memory operator quite a bit is if we're going to be using them in a black box, make sure that it has a unique operator name, but also unique variable names. That can cause some confusion if you name your variables something simple like size. It might get a little confusing with a lot of memory variables in here. If you've got multiple ones named size, you might not know exactly what it is you're dealing with, especially in a black box. So what we tend to do is name it in accordance with its black box. So it might be example 2 size. So now we know that this example 2 memory value definitely lives inside this example 2 dynamic set. So just kind of making a logical correlation between those somehow so we can easily keep track of these. And then that way when we save this out as a black box, then this memory value is self-contained within that black box, and it has its own unique variables. Okay, so that's it for Pitfalls so far. Let's go ahead and move on.